Now let's take what we know about polygons and look at geometric probability. And here's the way geometric probability works. Here's the way the game is played. Let's suppose that we have some region here. Like in this case, we have a rectangular region. And inside that region is a smaller triangular region. And let's suppose we just start selecting points at random. Okay. So I select a point here, here, here. These are just random points, completely random. Well, you notice a lot of the points fall outside the triangle. Some fall within the triangle. Okay. We want to know, well, what is the probability that a randomly selected point will be inside the triangle? So here's what we do. We take the big area. The big area is the area of this triangle, and you notice it's 1, 2, 3, 4, 5, 6. 6 times 1, 2, 3, 4, 5, 6, 7, 8. 6 times 8. And then we calculate the area for the numerator, the area of the triangle. So we got 1, 2, 3, 4. 1/2 base times the height. 1, 2, 3, 4, 5. Okay, so we get up top 10, and on the bottom we get 48, or in other words, 5 24ths. Okay, so the probability that a randomly selected point will lie inside the triangle is 5 24ths. Okay, so that's the way geometric probability works. Now you can have more complicated ones. For example, let's look at this next one. We've got a regular hexagon inside of a circle here. Okay, and what I want to do is I want to select a random point, just a randomly selected point, and I want to know the probability that it will be inside the hexagon. That's what I want to know. Now, first of all, the area of the circle, which is going to be on the bottom, is going to be pi r squared. So the area of the circle is pi times 4 squared, or in other words, 16 pi. That's what's going to go in the bottom. And then the smaller area is the area of the hexagon. And we know that the area of the hexagon, the area of hex, is going to be 1/2 the perimeter times the apothem. Yeah. Now, remember that you might be wondering, well, where did we get this 120 here? Where this 60 come from, etc. Well, remember that the interior angles are calculated this way. You take 180 times the number of sides of the polygon and subtract 2. So that would be 4 times 180, which would be 720. And then you can get the, if you divide that by 6, you get the 120 right there. Now what we're looking at is, so we've got these triangles here. And these turn out to be equilateral triangles. So each side is 4. Okay. And in fact, this triangle that I get here is an equilateral. And this side is going to be bisected by this height. So you get a 30-degree angle there and a 60-degree angle here. So if we want to get the apothem, we know that the side opposite the 60-degree angle is half the hypotenuse times the square root of 3. So we've got 1/2, half the the perimeter times 2 square roots of 3. That's this apothem right here. Now I need to get the perimeter. Well, the perimeter is 1, 2, 3, 4, 5, 6. 6 times 4 is 24. So we get 1/2 24 times 2 square roots of 3. So the probability of this is the area of the hexagon. So the probability of your randomly selected point falling inside that hexagon is going to be 1/2 times 24 times 2 square roots of 3 over 16 pi. And of course you can simplify that, but that's the ratio that you're looking at. And of course, I guess an easy way to simplify that, this is 24 square roots of 3 over 16 pi. And then 8 will go into 24 3 times. So this is 3 square roots of 3 over 2 pi. There you go. And that would be your probability. So that's the way the game is played for geometric probability. You have to calculate, you have to figure out what the area of each of the regions are, and then put the bigger region area on the bottom and the smaller on top.